So for this lesson, what we're going to be talking about is multiple motion. If you haven't done so, I would print off a PDF of these notes so you can follow along with the question as we're working on it. So the reason this is multiple motion is we're looking at two things. In this first question here, Billy is dragging his dog along. And I want you to notice that Billy is dragging the dog at a bit of an angle. Okay, so the force isn't up, down, left, right, it's on an angle. That's going to be important. So we've got two motions here. In the first one, Billy is pulling the dog in the wagon. And in the second one, Billy has let go of the wagon and the wagon is just traveling on its own. So there are two motions, one where Billy's pulling and one where Billy's not. So just like all the other unit questions we've done in this unit, the first thing we need to do is we need to draw a free body diagram. So we've got our free body diagram right here. Now we know the mass is 20 kilograms. Now what does this have to do with Billy? It doesn't have anything to do with Billy. The focus of this free body diagram is going to be on the wagon and the dog. So as such with the dog, we've got our force gravity, we've got our force normal, we've got our force applied. Now our force applied here is going to be on an angle. Now we know according to this question that it is at 30 degrees above the horizon. So what we're going to do is we're going to have a piece here. We're going to call this force applied and we're going to put an H here to represent the horizontal. Okay? Because we know this all force applied, part of it is resulting in the wagon being pulled forward and part of it is being pulled up. So our force applied in the vertical. The last thing we're going to do is we're going to talk about friction. Now, as we know, friction runs parallel to the surface. So even though the force is on an angle, the friction is not going to be. Next thing we need to do is we need to do a T-chart. So we're going to draw this out and put it out here. Okay? And we will represent our vertical and our horizontal. And now in the vertical right here, we've got our force gravity. Our force gravity is equal to mass times acceleration. So if the mass of the dog is 20 and the acceleration is 9.8 due to gravity, therefore this makes it 196 newtons down on the dog. What other forces do we have in the vertical? Well, we've got our force normal. Now you may be thinking that the force normal is also 196, but it's not. And the reason why that is that's due to a force applied in the vertical. Okay? Now we know the force applied we're putting on this cart is 80 newtons. Okay? But it's not going to feel all those 80 newtons. It's going to be sine 30. Because yet again, we're on a bit of an angle here. So that makes it 40 newtons up. So now we've listed the three forces that are acting in the vertical. So therefore, our F net has to be equal to our force gravity, our force normal, and our force applied in the vertical. Now let's use a little bit of common sense for a second. Do you think this 40 newtons is going to be enough to overcome the force of gravity, which is 196 newtons? The answer is no. So therefore, we can establish that our net force is going to be equal to 0. Now, if we know this is going to be 196 down, so we'll say a negative 196, we've got our force normal, and we've got the force applied in the vertical. Therefore, we can figure out that our normal force is going to be equal to 156 newtons up. What that basically means is you've got the 40 newtons from the applied and 156 from the ground is counteracting gravity, so the object doesn't, so in this case, the cart doesn't accelerate through the ground. Now let's talk about motion in the horizontal. We've got two motions. We've got our force applied in the horizontal. Now in this case, again, the answer is not going to be 80. It's going to be 80 times cos 30. So therefore, we are going to determine that the force applied horizontal on this cart is going to be 69.2 newtons to the right. Our force friction in this case is going to be equal to mu force normal. Now we know the mu in this case is going to be equal to 0.3. And we know the normal force from what we figured out here is 156. Therefore, our normal force is going to be equal to 46.8 newtons. And therefore, it's going to be to the left because it's going to counteract the force. So we've now listed our two forces, so we're going to use the same process. We know that the net force has to be equal to the force applied in the horizontal and the force friction. So we've got 69.2 minus 46.8, which makes our answer 22.4 newtons to the right. So we've done the first three steps of the process. We have drawn the free body diagram, we've listed out our forces, and we've determined the net force. And we know our net force is going to be equal to 22.4 newtons to the right. So now the next thing we'll do is we're going to figure out the acceleration. So we know our net force is equal to 22.4 newtons to the right. The mass of the dog is 20 kilograms. We don't know the acceleration, but we know that F net is equal to ma. So 22.4, 20a, which is going to make my acceleration 1.12 meters per second squared to the right. Last thing we need to do is the question's asking how long is this going to take. So we list out that our time is unknown. We're going to assume that we're pulling the dog from rest, so v1 is equal to 0. We know the acceleration, because we just figured it out, is 1.12 meters per second squared. And what we want to do is figure out that the final velocity, or v2, is going to be equal to 5 meters per second. So then we use our kinematics to figure out that a is equal to our change in velocity over time. So we plug that in and determine that our time is equal to 4.46 seconds. Now, all that we've done here is just when Billy's pulling the dog. So when we get to our next question here, Billy is no longer pulling the dog. This means this is where people get the questions wrong. So this is the key. We've now changed the circumstances, which means we need a new free body diagram every time. So we're going to draw our free body diagram here in 20 kilograms. There's no longer a force applied. All we've got is force gravity. We've got our force normal. And we've got our force friction. Don't fall into the trap of reusing information from before. This is a new question, so we need to treat it as such. So therefore, we're going to do a new T-chart, where we're talking in the vertical and we're talking in the horizontal. Now in the vertical, we've got our force gravity, which is still equal to ma. So 20 times 9.8. So therefore, it's going to be equal to 196 newtons down. There is no force applied this time, so therefore, we still don't know our force normal, but we've only got two forces when it comes to our net force. Our net force is therefore going to be equal to force gravity plus force normal. Yet again, the net force is going to be 0, so therefore, if we know that the force gravity is negative 196 newtons up, we can therefore figure out that our normal force is going to be the exact same value, 196 newtons up. This is key. You'll notice that the force normal in our last question was 156. Now it's 196. That means that our force friction that we're going to have to figure out is going to be new. Okay? The coefficient of friction hasn't changed. It's still 0.3, but our force normal is going to be a different value, which means that this force friction is going to be equal to 58.8 newtons to the left. Since there's only one force, our net force is going to be equal to 58.8 newtons to the left. So now what we can do, since we have a new net force, we can figure out our new acceleration. So net force is equal to 58.8 newtons to the left. Mass is still unchanged. Acceleration is unknown. And our F net is equal to ma. So when we plug in those values, we see that our acceleration is equal to 2.94 meters per second squared to the left. So because this is a multiple motion, if you remember previously, the final velocity or the second velocity from the first part is equal to the first velocity to the second part. So we know that this time our initial velocity, since Billy's been pulling it, is at 5 meters per second to the right. We know the wagon eventually, due to gravity, is going to slow down, so this will be 0. Our acceleration is equal to 2.94 meters per second squared to the left. Now we can't work with this because right and left are not the same direction, so we're just going to change this to negative 2.94 meters per second squared to the right. Still trying to figure out time, and our formula is going to remain the same. So therefore negative 2.94 is equal to 5 over t, which makes our t 1.7 seconds. So we now know the second motion is 1.7 seconds. So if the first motion was 4.46 seconds, and the second motion was 1.7 seconds, then therefore 1.7 plus 4.46 means our entire process is 6.16 seconds.